Now that we've learned about Ohm's law, V equals IR, I want to go back and look at what happens when we have combinations of resistors. And first, I want to remind us that we already know something about series combinations from working with capacitors. What we knew when we worked with capacitors was that if I have two things in series, the voltages must add up. So the voltage drop across the first capacitor plus the voltage drop across the second must be the same as the voltage the battery is giving us. We also had that the charge had to be the same on those two because charge is conserved after all, so whatever charge came off of C1 had to go on to C2, and that's the charge that came out of the battery to begin with. So the first of these is a statement of conservation of energy. Voltage is related to potential energy after all. And the second is a statement of conservation of charge. Well, now we're going to switch these guys out and put in resistors instead. And the way we denote resistors in a circuit is with this little zigzaggy line there. So I've got a resistor R1 and R2, and I'm going to put numbers on those in a minute here, but for now let's just leave them as variables. And the key thing about this is, with a capacitor, the charge just flows into the capacitor and sits there. So Q is a static number. But here, the charge is just going to keep on flowing and flowing and flowing. So I can't talk about a resistor having a charge on it. Instead, what I have to talk about is how much charge flows through the resistor as a function of time, which we know now is what's called the current. So instead of charge being conserved, in some sense what I'm talking about here is current is conserved, which is really the same thing actually. So I have I1 is I2 is equal to the total current in the circuit. And I'll show you how that's applied in a second. In any case, in a series combination, the voltages must add up, the current must stay the same. So, if I look at that, take that V1 plus V2 equals V total, and plug in V equals IR, what I have is I1 R1 plus I2 R2 equals I total R total. Now the I's are all the same, so I can divide them out, and now I get a rule for adding up resistors in series with each other. R1 plus R2 is equivalent to R EQ, the total resistance of the circuit. In other words, I could take R1 and R2 out and replace it with some resistor that is the sum of the two and have the exact same effect. Notice this is different than it was for capacitors. In capacitors, we added up the capacitors as reciprocals when we were in series. Now when we're in series for resistors, we add them up straight. Don't get confused by this and actually try to understand where it comes from. But one way or another, it's a rule. Just get used to using it. So, let's use it. Let's say I've got a 9-volt battery and I hook up a 50 ohm resistor and a 250 ohm resistor in series with it. If I do this, the total resistance is going to be 300 ohms, so it is effectively the same as if I just put a 300 ohm resistor in there instead. That means I can go calculate what current actually comes out of the battery. I can do a V equals IR for the whole circuit. V equals IR means that I equals V over R, and I get 30 milliamps of current that comes out of the battery that goes to these two resistors that I've got in series with each other. Now we can look back at the two resistors again, and that 30 milliamps must go through both of them. Right side of the screen does say I2 equals I1 equals I total, so the current that goes into the first must go through the second, and both are that 30 milliamps. Now I have V equals IR for each of the two resistors separately, and I can calculate how much voltage is on the first one and how much voltage is on the second. So V equals IR on the first one gives me 1.5 volts there. V equals IR on the second gives me 7.5 volts there. Notice the 1.5 and the 7.5 add up to be 9, so everything's copacetic here. The V1 plus V2 does in fact equal V total, and I1 equals I2 equals I total, and V equals IR is behaving itself for every element of the circuit, so everything's good. Notice that what happens here is I have a 9-volt drop that I have to get through for the whole circuit, and most of it is going to drop on the bigger resistor. If the two resistors were equivalent, the drop would be the same on both. If one resistor is bigger, more of the voltage is going to get held up on that one than on the other one.